Okay, so you said you were robbed. Yes, I was walking in the street and then this thing, this electron, it just waved friendly and took my phone. Sir, I'm going to show you a lineup. Could you please identify the robber? But they're all the same. Welcome to Fundamentally Explained. Here we try to uncover the mysteries of the smallest building blocks of nature. Our best understanding of these building blocks, or particles as they are called, is encoded in a theory called the Standard Model. It contains 17 unique particles, and one of these particles is the electron. Electrons form electricity, are key components to atoms and molecules, and essentially govern all of chemistry. Electrons, like all other particles, have very specific properties. They have a very specific mass, for example, and a very specific electrical charge. These properties, and all others, are exactly the same for all electrons. Like, exactly the same. This makes every electron absolutely identical to all other electrons. Experimentally, this is super nice. It allows you to find out whether or not a particle is an electron. Theoretically, however, you can ask the reasonable question, but why? How can that be? Even the most precise factory in the world churns out its products with ever so slight differences. But apparently nature can create electrons that are identical in every way imaginable. In this video, we will explore exactly that mystery and try to answer the question, why are all electrons the same? To understand why all electrons are the same, we need to get an answer to an even more fundamental question. What are electrons exactly? The answer to that question can be found in what is possibly the most ill-explained experiment in all of physics. The double slit experiment. The idea of this experiment is actually rather simple. Fire electrons in the direction of a plate with two small slits in it, and see where they end up on a screen that is placed behind the slits. If electrons are like small little objects, they would create the image of the two slits on the screen. When the experiment was performed, however, the pattern was this. Not exactly a pattern of two slits, is it? This is what is called an interference pattern, and it proves that electrons are not small little objects, but in fact waves. I know this sounds weird and counterintuitive, but let us assume for the moment it is true and try to understand the pattern that we see. In the experiment, the electron is fired towards the slits. Let us assume the electron is indeed a wave and have a look at the top view of the experiment. Something like this. Now, having fired the electron towards the slits, after it passes through the narrow slits, the wave expands in a circle-like pattern from both slits towards the screen. These circular waves can strengthen each other at places where they meet, at places where their troughs meet or where both their crests meet. At other places, the opposite happens. The crest of one wave meets the trough of the other. When this happens, the waves essentially cancel each other out. This interference is characteristic for waves and can indeed be seen on our measurement screen. A nicely repeating pattern of places where there are many electrons and places where there are very few of them. This shows that electrons are indeed waves. Okay, so electrons are waves, but if we look closely at the interference pattern, we see that it consists out of dots. Each dot is an electron that hit the screen, but that is not what you would expect for a wave. Wouldn't those give a more nice smooth pattern? Does this mean that electrons are small little objects after all and not waves? What is going on? Turns out the answer is some quantum weirdness. That's what's going on. Using the idea that the electron is a wave, we can fully explain the pattern, everything that's going on before the electron hits the screen. When it eventually hits the screen, where the measurement of the position of the electron actually takes place, the wave seems to collapse. It chooses a position to narrow its wave down to. The act of measuring the wave changes the wave. As we can still see the interference pattern, we know the collapse is not random. The electron is very likely to turn up where the wave is strong, and very unlikely to be found where the wave is weak. Now, I can understand if this all sounds a bit strange, but that's only the case because it is strange. And we can make the experiment even stranger. Let us take the same experiment, but now detect the position not only at the screen, but also at the slits. This forces the wave to collapse, choosing not only the position at the screen, but also at the slits. As a result, the wave does not go through both slits anymore, but effectively chooses a slit to go through. After this choice, it waves on until it hits the screen, where the wave again collapses into a specific position. As there is no wave from the other slit to interfere with anymore, the pattern on the screen is just a blurred image of the two slits. The big question is then, of course, how can the act of measuring the electron change the wave? And I would love to tell you the answer, but I don't know it. Don't close the video. Nobody knows the answer. It's one of the biggest mysteries in modern physics, and as with any other good mystery, people have given it a name. The measurement problem. True, it's not the most catchy name ever, but I guess it's better than a more human name. This year's Nobel Prize for Physics is awarded for finding a fundamental solution to the long-standing problem of Steve. On the other hand, we could have also given it a much lamer name. Imagine we would have called it something as stupid as the Standard Model. That would be totally ridiculous. Who would come up with such a lame name for something this important and big? That would be... When we looked at the experiment, I said that this experiment is possibly the most ill-explained of all physics experiments. The reason is that especially when we detected the position of the electron at the slits, an interpretation as the electron changed into a particle seems to make kinda sense. It would explain the new pattern. So, most of the time you hear the experiment explained as electrons sometimes behave as particles, or rather objects, and sometimes as waves. This is what we call the wave-particle duality. Your measurement at the slits simply changed the wave into a particle, which explains the new pattern we see when we measure the electron at the slits. Although this interpretation indeed solves the problem, it also makes the electron into some kind of magical entity. An entity that can choose whatever it wants to be. Although this is of course very empowering for the electron, and don't get me wrong, all power to and from the electron, it would also mean that we would lose all hope of ever being able to understand what is happening. Luckily, our understanding of the experiment and of electrons has advanced since then, so that we now know that electrons are always waves. What we called a particle thus far is just a highly localized wave. Yes, we get this mysterious measurement problem for it in return, but at least now we can predict up until and right after the measurement at the slits how the electrons in our experiment behave. This raises, however, a new problem. If electrons are waves, what are they the waves of? What exactly is waving? Sound waves are waves of density in air. Water waves are, well, waves in water. In a similar manner, electrons are waves in what is called a field. A field is something kinda a bit like a pool. Just like a pool can be filled with water on which waves can exist, so is the universe filled with an electron field in which particle waves can exist. All electrons everywhere in the universe are waves in this single electron field. And it is this fact that causes all electrons to be indistinguishably the same. Yes, we are finally getting to that answer. Electrons are the same because they are waves, and these waves get their properties from the field that they exist in. To go back to the a field is like a pool idea, the behavior of the waves in the pool is determined by the stuff in the pool. Waves in honey behave differently than waves in water, or waves in sand, or whatever other stuff you could fill your pool with. The medium determines how the waves behave, and so does a field. The fact that different particle types behave differently and have different properties is therefore because their fields differ. Each of the particle types we know has its own field. There's a field for particles that form light, a field for Higgs particles, and so on for all of the 17 particle types in the Standard Model. All particles of a similar type are identical, therefore not only holds for just electrons, but for any of the particles that we know of. So, summarizing, electrons are waves of a field, a pool-like thing. The pool has properties that determine the properties of the waves in the field. As these waves are actually electrons, each electron has the same properties, making them absolutely indistinguishable from each other. So that's it, an answer to the question why all electrons are the same. I do hope you liked this explanation in this video. I spent more time than I'm willing to admit on the animations. And if you did, give it a thumbs up and leave a comment. I would love to hear from you. For example, on what got you interested in particles. Was it your high school teacher or a nice YouTube video? Maybe even from my channel? Oh, and while you're down there, subscribe and ring the notification bell thingy down below if you don't want to miss any of my upcoming videos. I have quite a long list of things I still want to talk about. Oh, and of course, no matter what the next video will be, I'll promise they will all be completely understandable, as they will be fundamentally explained. See you next one. But they're all the same. Sir, just identify the robber, please. How do you expect me to do that? I thought you were robbed by an electron. Yes. Did you see the electron? Yes, but shouldn't you then be able to identify which one robbed you, sir? No, they are all the same. They always are, by definition. Okay, I see they look very much alike, but... Okay, so I have the same problem. What if I point at the wrong electron and an innocent electron is charged? Sir, they are already charged.